This video provides a short demonstration of our least squares module. This module can be used to help students understand how the ordinary least squares method estimates a regression line. The project in a single variable regression is to pick the best line to fit the data. So we should start with some data. And if we click this New Points button, we get a randomly generated set of 5 points, where we can think of the y-axis giving us an outcome variable that's related to a regressor on the x-axis. And we can have as few as 4 points or as many as 10, so students can play around with different options. Let's go ahead and start with 6 randomly generated points. All right, let's go with that one. When I say pick the best line, there are 2 components I need to consider. 1, how do we define a line? And 2, how do we define best? So regarding the line, since we're starting with an assumption of a linear relationship, a line is simply defined by the equation y equals mx plus b, an equation which most students recall from middle or high school. In this equation that defines a line, b is the intercept, or in regression we tend to call it beta 0, and m is the slope, which we tend to call beta 1. So when I say pick a line, I mean pick an intercept and a slope. So we can do that here. Let's go ahead and look at our data, and I'm going to guess that the best intercept is around 4, so I can pull a slider over to around 4, and then I'm going to guess a slope less than 1, but still positive, so I'm going to try 0.5. Now, before I plot my line, I'm going to think about how I'm going to judge it. Right? And when we use the OLS estimator, we decide that the best line is one that minimizes the sum of the squared distances of all points from the line. So let's go ahead and plot our guess. Right? And what we see now is that each point, we can find the distance of that point from the line. Right? We see that for each point. And at this point, you've probably explained to students that if we simply use the distance in the y direction of each point from the line, the positive and negative distances would cancel out, and the best possible line would always just be a flat one at the average value of y. So to get rid of that problem, we decided to square the distances and try to minimize that sum of squares. And so plotting the square of each of these distances allows students to visualize the project of minimizing the squared distances. And we can see that our current sum of squares is 105. And we can think about what could we do to potentially reduce the sum of squares. I'm going to think maybe if I increase the intercept just a little bit, and in fact do see as I increase the intercept, I was decreasing the sum of squares, and maybe the slope is a little too steep. So let's decrease that. And I see that I've now decreased my sum of squares to 98. But that makes me wonder if now I maybe need to increase the intercept. And I see that as I do that, I am in fact reducing the sum of squares. And this can actually be a kind of fun activity with students of sort of iterating around picking the intercept and slope. And now I've started to wonder if I'm actually quite bad at this, and I should maybe have had an intercept that was quite a bit higher and maybe a negative slope. Right? So after iterating with this for a while, we can go ahead and click the Reveal the Least Squares button, and the application now plots the actual, oh wow, looks like we were pretty close there at the end, plots the actual ordinary least squares regression line. We can explain to students that while it may be fun to play around with this guessing game, it's ultimately far more efficient to use the equations for beta 0 and beta 1, for example, using calculus, that minimize the sum of squares. And it's exactly those OLS estimators of beta 1 and beta 0 that our statistical software uses when we estimate our regression coefficients. And again, this is the kind of activity that students find fun to, pick different points and start over.